Okay, I think we should get started. We take some grace for people being late, traffic and so forth, so I think that's enough. All right, so thanks a lot for coming tonight. I've got a couple of announcements and introductions. Let me start with introducing Deborah before she sits down, the hostess from Plum Grid here. Deborah, you want to just say something quick? Tell everybody what is Plum Grid, in case somebody doesn't know.
Sure. So Plum Grid is a software company. We do have an overlay technology for networking. So we do OpenStack, we do just general cloud, we do containers. We work with the Linux Foundation through the technology which is IOVisor, which is the IOVisor project. So it's a technology which we open source with the Linux Foundation. That's the high level. If you need the restrooms, I've said it multiple times, they're outside. Feel free to get up if you need to go.
So we have Deborah to thank for hosting. She did a lot of work in person here. Thanks so much to her. And then I want to introduce Joel, who came tonight. Joel's going to be speaking tomorrow night. So if you have any questions about his talk, or Joel, you want to say something real quick about what you're talking about tomorrow night?
Yeah, so, sure. So tomorrow I'm going to be talking about debugging real-time issues in Linux systems. So I'm going to be like, I try to make it a recipe kind of talk, like where I show you like real problems that I've seen and like things you can easily do to like find those issues and fix them. And I kind of show you like output of various tools, and I show you like code examples and stuff like that. So hopefully you like it. Yeah.
Okay, so I think everybody's probably a member of the meetup or so forth. So we have almost 3,200 members of the meetup now. So that's great. So when I started the meetup years ago, it was mostly so I could invite people to give talks that I wanted to hear. So I had an excuse for, hey, come do a talk. So I did. And both tonight's talk and tomorrow night's talk really fit in the sort of stuff I'm personally interested in. I've been doing a lot of embedded real-time Linux for many years. So I'm excited about these. Also, by the way, I just want to put a little comment in there. If you feel generous and you want to contribute to the meetup, that would be cool, because actually I had to pay for renting the chairs and stuff like that. So that's like $400 from the group to pay for these 2 nights. Okay, so let me introduce Alison, who I've known for years, and I've heard speak before, and I'm looking forward to her talk. I'll let her describe what she wants to do with questions or whatever. So I think we're ready.
We're ready.
All right.
Well, thanks very much, Kevin. Kevin was somebody I met when I first started becoming a Linux developer, and he told me about cscope and LWN, so I've been grateful to him ever since. So this talk is a practice talk from my presentation in Embedded Linux Conference Europe in about 2 weeks, as is Joel's talk tomorrow night. And the time slot I was given by the conference is 110 minutes, to my surprise. So you'll be relieved to hear that this talk is not going to be 110 minutes long. But because I'm excerpting a shorter talk out of a much longer talk, this is not going to be the most smoothly flowing presentation of all time, for which I apologize. I'm going to skip past half the material. If you see something go by you really want to discuss because you're interested in it, or if you have a question, please do ask. For me personally, a big part of the point of giving this talk is so that people can tell me now if I'm saying things that are actually false. That would be wonderful. Or if something's completely unclear. So I have 2 pieces of hardware I can show demos with. We'll just see how much fits in before most of the people seem very restless or asleep. So there is a demo at the end with eBPF, which if you can read that diagram there. Which I originally learned about from Brendan Blanco, who is an employee of PlumGrid, and that talk at Southern California Linux Expo in January was part of the inspiration for this one. So whatever else happens, I will at some point just skip to that demo to show that I paid attention to the advice Brendan gave me and actually got it working. So with that, let's get started on actual content. I'm going to start by talking a little bit about hard IRQs and the kinds of hard IRQs, but I find soft IRQs and the problems associated with them much more interesting. So I am going to skip most of the material about non-maskable interrupts, interprocessor interrupts, all that kind of stuff. But as I said, feel free to complain. It should be obvious. These slides are posted, and the magenta text is hyperlinks. And so I fortunately still have code here on my laptop that I haven't pushed to GitHub, but I have some stuff there that could be useful to somebody already. So, we talk about what are IRQs and why do we have them. I'm mostly going to skip the part about kinds of hard IRQs, I think, and get to soft IRQs. I've been working on real-time Linux debugging, as has Joel, so we may have some overlap between our talks. I don't know. Maybe I'll allow him to skip some of his introductory material tomorrow night, but the difference between soft IRQ handling in real-time and non-real-time Linux is one of the major differences between them, and it's very hard to get right. So actually a problem I had at my day job inspired this kind of investigation I've done. So in the full version of this talk, I'm giving some examples of studying the behavior of IRQs with K-probes, J-probes, event tracing, MP-stat, which is a regular util Linux tool, and of course eBPF that I already mentioned. And the example that I investigate in depth, which is about the second half, is about understanding and tracing when network packets that are received on Ethernet are switch over to what's called NAPI, the new API it's called. So NAPI now, somebody in the audience probably knows, is I think 12 years old or 8 years old or something like that. But at the job I had, we had a problem where our system melted down if you pinged it, if you ping flooded it. And our system is a safety control system. And so we obviously couldn't ship something that if someone ping flooded it, it died. And so I spent a lot of time, not with my work hardware, but with this laptop and this board, understanding how NAPI really works in the real-time kernel. So here's some stuff that I could potentially talk about. Why are atomic operations expensive? What is the current task? In whose context an interrupt runs? And the thing I really spent a lot of time on, when do we switch from hard IRQ processing of Ethernet packets to NAPI? So let's start at the very beginning. This is my pictorial summary of interrupts. They tend to get split into two parts as far as their behavior in the kernel. There's what's called a top half, which all the top half, or hard IRQ as it's sometimes called, does is it schedules the soft IRQ, or bottom half, and then tells the interrupt controller that it has serviced the interrupt. So basically the top half just kicks the can down the road figuratively and tries to wake up the soft IRQ that actually does the real work. So an example that's pretty obvious would be, let's say you insert a SD card into an MMC drive. Well, the card detect line will fire off an interrupt that tells the block controller driver that there's an SD card. And usually the driver will just start a soft IRQ that wants to interrogate the card and try to mount the file system. Basically try to start the block layer that creates memory objects for the device. But the block layer is very slow, so the way we handle IRQs with low latency is we have the hard IRQ return pretty much immediately, and when the system is less busy, we run the block layer that actually mallocs, which is a slow operation. So why do we need interrupts? Why not just, poll all the devices, that is, with a timer, periodically go and ask all the devices if they need any services from the kernel? This is the most basic fact about interrupts. Presumably everybody knows the answer to this, is that a lot of devices never need any service. I mean, I have maybe FireWire on this laptop and I've never used it, so having the kernel pull the FireWire device wouldn't be very useful. And then other devices really want low latency, but they're low CPU usage. So the canonical example people always talk about is hitting a key on the keyboard. This happens from the point of view of a gigahertz processor extremely infrequently, but on the other hand, the user gets very frustrated if they're typing and the processor's busy and nothing happens. So we have interrupts so that the processor can react pretty much instantly to the IRQ generated by the keystroke, and when it has time, which is, microseconds or maybe milliseconds at worst, it'll print the character on the screen with the T2I driver. So, of course, real-time operating systems that don't have a process model or a bootloader are in a different situation. Actually, though, when I started looking into this, I was surprised to find out that U-boot actually does have some interrupt support. I think primarily because PCI, PCI doesn't really work without it. And skip past this. So let's talk about what kinds of IRQs there are. I already mentioned hard IRQs, which are the fast response of the kernel to acknowledge an event, and then the soft IRQs, which are the actual servicing of the device that the hard IRQ schedules. And tasklets are another kind of hard IRQ. There are IRQs associated with system functions like timers. There's a special soft IRQ for RCU, which some of you may know. Read, copy, update. I think that's right, read, copy, update. There's network IRQs, which is what I'm mostly going to talk about. So those are, block layer IRQs and network IRQs are triggered by a device, whereas an IRQ for the scheduler or a timer need not actually correspond to an actual device event. And there's all kinds of complexity with shared interrupts, and many systems have multiple interrupt controllers. But before everyone falls asleep and this gets too boring, I'm going to actually show you some of what I'm going to talk about. So I'm going to boot RT Linux on my Freescale IMX6 board. which is a popular automotive processor. It's going to ship in a lot of cars. Since I've been working on automotive and truck Linux for a few years. I think I have a networking problem. Don't need fancy tracing tools to figure that one out. I have to try this again. Much better. I found a new way of tracing network problems. Look at the cable. So here's the most obvious way to look at interrupts. Hopefully this font is big enough for people to read, I hope. Not big enough to stay on the screen, but so proc, of course, is the virtual file system where the kernel publishes statistics and information about what it knows about the hardware and what it's doing. So here we have on the left the number that the kernel is using for an interrupt. We have which CPU is receiving which interrupt. We have the name of the interrupt controller, which could be, for example, the generic interrupt controller, which is ARM. We have the GPC, the general power controller, and we have some GPIOs. Can anyone think of why interrupts would be serviced by the general power controller? That sounded odd to me when I heard it. Yes.
To be able to wake up the device from low power state.
Exactly, yes. So if the general power controller didn't know about interrupts, it wouldn't be possible to have a button wake up the system. So on the right here are the names of the devices that the interrupts are listening to. Some of them are buttons, a serial port, storage device, Ethernet, and the one I'm actually interested in for the purpose of this talk is this one, which is the Ethernet interrupt that's firing when the device that net booted is reading it through the file system and when packets are coming in. And you can also see down here at the bottom are some block layer, well, some storage device interrupts and so forth and so on. You can see whether the interrupts are level or edge triggered. The number there next to the level or edge is the interrupt controller's own number for the interrupt.
Are you sure you want that Ethernet one versus the other one?
I've been working on this project since March. So probably. And then down here at the bottom we have the interprocessor interrupts, which are interesting in their own right, but which probably don't have time to talk about. So that's on ARM, 32-bit ARM. Now
Can
let's
you
go.
talk about the difference between the two Ethernet ones?
You know, I have not really been able to figure that out, even by reading the processor manual. So one is hooked to the general interrupt controller, and one is hooked to the GPIO, and I have never seen a hit on the second one. Because it doesn't do anything, I haven't been able to figure out what it's for. At first I thought it must be transmit and receive, but it wouldn't make sense for them to be hooked up differently. Anyhow, this is, if anyone knows, that would be great. But good question. Okay, so that's that's what the proc interrupts looks like on 32-bit ARM. Let's look at it on the laptop here. And so now this is obviously x86-64, and so, oops, you can see that the names of the interrupt controllers are different on x86-64. There's a lot of PCI devices. Interesting thing going on Intel devices, of course. Just to make one comment about strange interrupts is some of the interrupts don't appear in this table because there's system management interrupts that come from, well, I'll talk about that a little bit more in a second, but so you can see all 4 cores are getting interrupts. Maybe that's, oh, and then a technique you can use to study interrupts is to use MPStat, which is a tool that comes in the util Linux package in Debian or Ubuntu. And all it really does is it formats this table from proc differently. So let's find my slide again. There we go. Okay. So I'm going to skip past this part about IPIs. This is just what I was going to talk about because it's interesting. There's a system management interrupt which comes from the tiny secure processor that's obfuscated from the Linux kernel intentionally by Intel, which has been identified by several people at talks at conferences like Black Hat and DEF CON as a security vulnerability. So there are interrupts in x86-64 that are outside that are intentionally hidden by Intel and their processors. There are new tracing tools that Stephen Rosted of Red Hat has just posted that at least detect them. So major difference between the real-time kernel and the mainline Linux kernel is threaded interrupts. In the real-time kernel, all interrupts are threaded. So what does that mean? So here, well, let's look at the board first. So here's another view of the interrupts, but now I'm using the process table to look at them. And in fact, you can see that each interrupt is running in its own thread. So the interrupts, each one separately, can be controlled via the tools that you use to control things in the process table. In other words, if you're used to the PS command, you know that this column here is the process ID. This column here is the parent process ID. This column here is the priority. And so one thing that'll jump out at you right away is the real-time threads have large negative priorities. So the way that the scheduler works in the real-time kernel is also different than in the mainline kernel, not surprisingly. But you can use renice or the command chrt, which I guess is change real time, to change actually the priorities or the CPU affinity of these threads. So what really makes the RT kernel work Joel can feel free to disagree with me, is that you can manage these interrupts by using the regular standard scripting and command line tools that Linux has, just like any other process on the system. And so for real applications, this is very important. For a safety critical system, we care a lot more about messages from the CAN bus, for example, than we care about touches on the touch screen by the user, right? So we not only want to prioritize the user space applications that fundamentally react to the interrupts, to the events that they signal, but we want to prioritize the interrupts themselves. And so a big part of working in RT is making that work. What's more surprising, if I go back here to my laptop, I should have made these different colors. Let's see. Maybe not. Well, I can make it big again. There we go. So that's my laptop. If we come back here to the laptop, you expect there's going to be nothing because so this laptop is running Debian stable, and it has the Debian stable 3.16 kernel. Pretty boring, right? So what's this going to show? Who has a guess? What the process table is going to show for IRQs for the boring Debian stable non-real-time kernel? Nothing? So I haven't talked yet about managing software IRQs. That's actually the next topic. There's always a K-soft IRQD running on each core, so that's going on here, and they cannot be moved or the way other processes can have their affinity set. There's also a way to force IRQs to run in threads, even in the non-RT kernel. There's something called, it's called IRQ force thread function. And so those, the Wi-Fi and the MEI, which is part of Intel's BIOS and ACPI table servicing, are actually threaded IRQs even in the non-RT kernel. What precisely the logic behind that is, I don't know. So for the most part, the threaded IRQs is a major difference between RT and non-RT. I'll just mention briefly the reason that atomic operations are expensive. Why don't we always use, yes?
Before that, could you clarify what does the flow look like compared to the typical top half, bottom half? What does the separate process introduce in the flow?
You mean
The processing of an interrupt.
so I'm going to talk about that
Okay.
at some length, hopefully.
That's good.
If I don't run out my time before that. Someone else got a question? No? Okay. I just mentioned atomic operations disable interrupts. So you might say, well, gosh, why don't I always use atomic inc or atomic dec instead of plus plus or minus minus? Why not? It'd always be safe. I'd never have, a problem with race condition. And the answer is that the atomic operations, if you think about how they must work, they can only work by disabling interrupts. Because if you didn't disable interrupts, you can't guarantee that all the processes running in this system on the 4 cores are going to see the same value of a variable. But if you basically prevent the other cores, say, from migrating the process or interrupting you in the middle of addition, which does happen in race conditions, you have to disable interrupts to prevent that. when you disable interrupt,